So now we will talk about Taylor's theorem. So let f be a function that maps from a to b to r and f belongs to c n minus 1, that is n minus 1th order derivative of f exists. C is a set of functions which n minus 1th order derivative exists, and f n minus 1th derivative exists and is continuous. So f belongs to C n minus 1, and since f n minus 1 is continuous, so fn exists. What is fn? Is the nth order derivative. So this is fn is nth order derivative, fn minus 1, fn exists, and fn minus 1 is definitely it exists and is continuous. Fine. So as per this is the definition of the function. This is the function f. These are its properties. Then f of then and let any let x and y be any numbers belongs to the domain of f. Then f of y can be expressed as f of x plus f of y, then f of so f first order derivative of f at x into y minus x divided by factorial 1 plus second order derivative of f at x into y minus x the whole square derivative of factorial 1, this is factorial 2 plus third order derivative of f x into y minus the whole cube divided by factorial 3 dot up to n minus 1th order derivative into y minus x to the power n minus 1 divided by n minus 1 factorial plus f of t f of n t y minus x to the power n divided by factorial n. So here so this is it, nothing more. So what is this f of n? We know what is f of n. It is nth derivative of f. And what is t? T is some value that belongs to x comma y, right? X is any unknown value that belongs to, so here we have a b b, below them, between them we have somewhere x and y, and somewhere in between x and y we have t. So fy can be expressed, this function, the value of function at this y can be expressed in terms of x in this fashion, and this last term for some t here. So this last term, this actually gives a return because t is unknown, so this is unknown. Now let y minus x is equals to h. We have written it several times. Y minus x square, yeah, like that. So let y minus x is equals to h. Then we can write f of y as f of x plus f prime x h divided by factorial 1 plus f double prime x h square by factorial 2 plus dot 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 plus f n minus 1 x h to the power n minus 1 divided by n minus 1 factorial plus fn t h to the power n divided by factorial n. So this is Taylor's expansion, called Taylor's expansion. It has some other forms also. Now we will look at them. So other form of Taylor series is in the last condition we had last form we had f belongings to c n minus 1. That means f n minus 1 n minus 1th derivative of f exists and is continuous, and fn exists. Sorry, fn exists. This implies that since fn minus 1 nth derivative exists, fn minus 2th derivative should also exist, and fn minus 1, as we saw, exists. So we actually give up some little bit of accuracy and write fy like this, equals to fx plus f1 x h by factorial 1 plus f2 x h square by factorial 2 plus dot 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 plus f n minus 2 x h n minus 2 by factorial n minus 2 plus f of n minus 1 t h to the power n minus 1 divided by n minus 1 factorial. That is, we knew that cn minus 1 f belongs to cn minus 1, but we consider that okay, and we got this condition now, fn minus 2 should also exist and fn minus 1 also exists. So we considered these two conditions instead of considering that f of n f n derivative of f also exists. We consider it like here, and we wrote it down in this way. So now one more thing. So we have here this written in this fashion. So we wrote that y is equals to x plus h. Fine, here h we got from here. So t and t belongs to x comma y. So we can write it like t is equals to x plus lambda h, right? This is x, this is x plus h is equals to y, t lies somewhere here, so is equals to x plus lambda h, and some fraction of h we add to this x and we get this t. So now we can write this as, okay, let's write it in next slide. So then we get this f of y is equals to fx plus f prime x h by factorial 1 plus f double prime x h square factorial 2 plus dot 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 plus f n minus 2 x h to the power n minus 2 n minus 2 factorial plus f n minus 1. For t we replace it with x plus lambda h n minus 1 factorial h to the power n minus 1. Now here we see that this is continuous, and this is continuous because f of n minus 1 is continuous. Fn was not continuous, but since f belongs to c n minus 1, therefore f of n minus 1, the derivative of f is continuous. So this function is continuous, and from Weierstrass theorem, and f also belongs to R, isn't it? Yeah, f actually this f domain of f is a b, and this belongs to RD. Yeah. So a minus b belongs to RD. So from Weierstrass theorem, f being continuous, f n minus 1 being continuous, and e that a minus b, that this is, let's call this set as e, is compact, that is it is bounded. We have bounded both a and b included, and so we see that the a minus b is closed because both the boundaries are included, so it is closed, and it is also bounded. It is also bounded, that is it is greater than minus infinity. I mean there is some, it is bounded between a and b, so it do not go to plus infinity or minus infinity. So we see that f and minus 1 also not goes to plus infinity or minus infinity, because it can only go up to, it is continuous, and its domain extends from a to b, so this is bounded also, this is also closed. So that's why from Weierstrass theorem its supremum and infimum exists, that is this can be, they have a maximum, I mean it is a constant, right? Maximum it is a constant, so this error basically is a function of this h of n minus 1. So we write it as small o h of n minus 1. So okay, sorry, forget about it right now. We will see about it in the next video.